All right, good morning, everybody. Hope everybody had a good spring break. Lost an hour of sleep. But yet you still made it here today, so that's good. Good. So last time we were talking about the chemistry of alkyl halides, and we're going to finish up today with talking about alkyl halides and their beta elimination reactions. But before we do that, I want to talk just a little bit about some review stuff here. So I've got two reactions. I've got an alkyl bromide in both cases. I'm going to react them with sodium cyanide. What do you think is going to happen? What do you predict will happen here? Take this alkyl halide, put it in some solvent, I don't know what it is, doesn't matter right now. Put in some sodium cyanide, stir it around, maybe heat it. What's going to happen? What kind of reaction? What kind of reactions can alkyl halides undergo? What have we learned? Substitution. Yeah, I heard somebody say it. Substitution reaction. What are we going to substitute? What for what? What do we need for a substitution reaction to occur? We need a nucleophile, and we need an electrophile, right? And we know that the alkyl halides are electrophiles. Nucleophiles will attack them. What's the nucleophile here? Which part is the nucleophile, the sodium or the cyanide?
Sodium.
Sodium has a positive charge, right? Does it have electrons around it? No. Nucleophile has to have what? A pair of electrons. What has a pair? Cyanide, right? So the cyanide is going to function as a nucleophile, and we're going to substitute this for this, right? And so we're going to get plus sodium bromide. We've got to have all of our charges balanced. What's going to happen here? Don't make it harder than it has to be. What's going to happen here?
It's not the same thing.
Huh?
It's not the same process.
It's not the same process, but it's the same end result. We're going to do a substitution, but it's not the same process, you're right. What are we going to substitute? What for what? Where's our nucleophile?
Side.
It's the cyanide. This is our electrophile, right? So we're going to substitute this for this again. And we're going to end up with, and again, plus sodium bromide. But how this happens isn't the same. We learned about two substitution mechanisms. What were they? SN1 and SN2. Right? SN1 stood for substitution nucleophilic unimolecular, meaning that there was the slowest step in the reaction only involved one species. And SN2 was substitution nucleophilic bimolecular, meaning that two things were involved in the slowest step of the reaction. What do you think this one is? Is this SN1 or SN2?
Is that SN2?
It is.
Oh, wait.
It is. This is SN2. This is an SN2 reaction. How do I know it's an SN2 reaction? I've got a good nucleophile because it's negatively charged, and I've got a primary alkyl halide, right? So the nucleophile will attack from the back. The leaving group will leave all in one step. Both species are involved in that single step, and I get the product. So what's this one? This one is SN1. How do I know it's SN1? Because this is a tertiary alkyl halide. The nucleophile can't get behind here and kick out the leaving group. It's crowded, can't do it. This is a two-step mechanism. Even though it says SN1, it's a two-step mechanism, right? This goes through what kind of intermediate? Carbocation, right? So whereas this was a simple thing to draw, this actually has to leave first, right? You get a carbocation. Now the cyanide can come in and attack, and you can get to the product. Right? The slow step is the formation of this carbocation. And we say that the slow step is called the rate determining step, or RDS. Right? We talked about that a little bit last time. So, you need to remember all of that stuff. You got to get back everything you forgot over spring break. SN1, SN2, alkyl halides. We have primary, secondary, tertiary alkyl halides. We learned about a solvent effect. We learned that there are polar protic solvents. We learned that there are polar aprotic solvents. We learned that polar protic solvents favor SN1 reactions, whereas polar aprotic solvents favor SN2 reactions. Okay? So we learned about a lot of those solvent effects as well and their role in this type of chemistry. So this was all substitution chemistry. The other thing that alkyl halides can do is eliminate. They can eliminate a halogen and a hydrogen atom to give an alkene. Okay, so you can make alkenes from alkyl halides, okay, if you have a base that can come in and remove the hydrogen and eliminate the halide. Okay? Notice that where the halogen is, we call that the alpha carbon, and everything that's attached to that must be beta. So we call this beta elimination. It's the elimination of a hydrogen and a halogen from a molecule. Notice where the double bond's going to be. It's going to be between the alpha and beta carbons. It's an easy way to make alkenes. The question you should have right now is, why is the base attacking the hydrogen and not just functioning as a nucleophile and displacing the halogen and doing a substitution? After all, the rule that I taught you was that all nucleophiles are bases. They're all Lewis bases, but not all Lewis bases are nucleophiles, right? So we have to find some type of base that won't function as a nucleophile, and there are those bases that exist that don't really do nucleophilic chemistry. Okay, they do the elimination chemistry. So this is called beta elimination. Okay? Some common bases that are used in these types of reactions are things like sodium hydroxide, potassium hydroxide, but you might think, well, those can function as nucleophiles. He just showed us before the break that you could take an alkyl halide and sodium hydroxide and you can make an alcohol, for example, right? And so those aren't particularly great bases for this dehydrohalogenation. The best one in this list is this potassium tert butoxide, this molecule. Okay? Looks like this. And it is a very good non-nucleophilic base that likes to do elimination reactions. Why do you suppose potassium tert butoxide doesn't like to be a nucleophile? In fact, if I took potassium tert butoxide and I placed it in with this, I wouldn't get the substitution chemistry. I'd only get the elimination. Why do you suppose that is? Whereas if I took that top and I reacted it with hydroxide, it would do the substitution reaction. So what's different between this and this? Okay, so there's the hydrogen on the hydroxides, but what's different? There is hydrogen. What's on the other one? An R group. Any R group? It's got a lot of stuff around it, doesn't it? It's bulky. It's very bulky. It doesn't like to attack another carbon atom because carbon has these other things around it. And you get two big things next to one another, they tend not to react. It's called steric hindrance. But what do we know about a hydrogen? Right? So if I had the hydrogen here, and I did that, right, to do the elimination, is hydrogen big or small? It's small. Big things will like to interact with small things just because of the crowding effect. Okay? So, potassium terbutoxide isn't going to attack the carbon because it'd get in the way of all this stuff, but it'll attack the hydrogen pretty easily because it's small. Okay? So you need to know the difference between a nucleophilic base and a non-nucleophilic base. And for the purposes of this class, there are others. We're going to limit it to potassium terbutoxide. Okay? We're going to say that that's the only non-nucleophilic base that you all are aware of. We'll keep it pretty straightforward. Okay? Now, if we take this case, where we take 2-bromo, 2-methylpropane, what we have down here, and I react that with sodium hydroxide, I'm going to get that alkene. That alkene forms very, very readily. It's a gas at room temperature. You can see it bubble out of the reaction mixture. But what you'll notice is that there's only one alpha carbon by definition because it's the thing that has the halogen. How many beta carbons do we have? We have 3. We have one here, we have one here, and we have one here. Now this one, they happen to show the hydrogen off of it, right? To show that you're eliminating here to give the alkene. But if I eliminated between here, would it give me the same product or a different product?
Same.
It would be the same. And if I eliminate from here, it's the same. Doesn't matter which hydrogen the base takes off. They're all equivalent beta carbons. Okay? So no matter which one loses the hydrogen, you get the same product. Is that going to be the case for this bottom 2-bromobutane? How many beta carbons do we have now?
2.
We have 2 beta carbons, right? There's my alpha carbon. There's a beta 1 and a beta 2. That's not beta. Right, that would be gamma. So there's only 2 beta carbons. So I could lose a hydrogen between beta 1 and the loss of the halogen on alpha, and I could get this product. Or I could eliminate the hydrogen on beta 2 and the halogen from alpha and get this product. Okay? Do you think I'm going to get those products in equal amounts? So if Alyssa came to the lab and did this experiment and then went and analyzed the results, do you think she'll get equal amounts of the first product and the second product? Or would you expect to get different amounts of each one? What do you think? There's only 2 choices, Pete. Equal or unequal. Take a chance.
Unequal.
Unequal. And unequal is the right answer. She will not get those in equal amounts. One of them will be the major product. One of them will be the minor product. Now let's predict. Which of these 2 constitutional isomers, the one on the left or the one on the right, would you predict to be the major product and why?
The one on the left has least amount of bonds, so it's easier to break apart.
Okay, that is a rational argument that is absolutely incorrect. But it's a rational argument. There's nothing wrong with that argument with what you know so far. This turns out to be the minor product. And this one turns out to be the major product. Can you explain that? the rationale that he provided is reasonable, right? We've got all of these bonds to hydrogen here. There's 3 hydrogens. The base has 3 options to pick off a hydrogen. On this carbon, it only has 2 hydrogens that it can pick off, right? So just statistically, you might think, well, it's more likely to pull off one of those hydrogens. Perfectly reasonable argument. It just happens not to be how nature works. So so it can't be that, right? He formed a hypothesis, we did the experiment, it turned out to be wrong. This is science. So now we have to find a different rationale. Why is it, do you suppose, that this alkene on the right is produced in the greater quantity?
Is it because the one on the right, where you have the double bond, there's equal amounts of both elements?
You're getting close. Wrong words for the right concept.
Is it because your hydrogens are balanced?
Again, I think getting to the kind of the same thing. Right concept, wrong words.
Symmetrical.
Again, right concept. But I can show you symmetrical ones that aren't. In fact, the one on the left, I can show you a point of symmetry as well, if we built a model. What did we learn about alkene stability? The stability of the carbon-carbon double bond. Well, we're going to have to go back a couple of chapters now, right? But we learned that the more substituents that are on an alkene, the more stable it is, right? So this happens to be a terminal alkene, right? So if I draw that out, 1, 2, 3, 4, that's that one. And if I draw this one out, right? This is a terminal alkene. This alkene only has 1 R group attached to it. How many R groups does this alkene have attached to it? It has 2. So the more substituted your alkene, the more stable it is. And it turns out that it's all about alkene stability. This is a rule that I don't know if they talk about in your book or not, but it's called Zaitsev's rule. And there's 2 ways to spell Zaitsev. There's one way with an S and there's one way with a Z. And I spell it with a Z. Zaitsev. And don't ask me to spell it right now. I forgot. Zaitsev. I think that's how you spell Zaitsev. Okay, he was a Russian. Came up with this rule. What do you think Zaitsev's rule says? Remember we learned about Markovnikov's rule, another Russian, in the formation of carbocations, right? Zaitsev's rule is kind of similar, except Zaitsev's rule states that when you have more than one beta carbon, the beta carbon with the fewest hydrogens, it has to have at least 1 hydrogen, but the beta carbon with the fewest hydrogens will always lose the hydrogen. Why is that? Because you will get the more stable alkene. Okay? That's what Zaitsev's rule says. So when you're looking at a problem like this, the first thing you want to do is identify that alpha carbon, and then every carbon that's attached to it is a beta. And ask yourself, which of those beta carbons has the fewest hydrogens? The one with the fewest hydrogen is going to eliminate it to give the major product. Okay? Now, in this reaction, what would I expect the ratio to be? If Alyssa came to the lab and actually did this, she would probably find about 10% of this and about 90% of this in her reaction mixture. Okay? You get a little bit of both, or you get some of both, you get a whole lot of one. That's the way I should word it. Okay? So this is called beta elimination. And it's a great way to make alkenes. We use it all the time. Okay? And just like in the SN2 and SN1, there is also E1 and E2. Okay, there's 2 different types of elimination mechanisms. You can have an elimination where the base and the alkyl halide are interacting in one step, That would be an E2 reaction. You can have an elimination reaction where the halogen has to leave first, you get a carbocation, and then it eliminates. That's called an E1 elimination, okay? So, the same thing with SN1 and SN2, it's just a little different in terms of the steps. It's kind of the opposite in terms of, you're thinking about elimination versus substitution. But just want you to know that there are two reaction mechanisms for elimination. There's actually 4 or 5 reaction mechanisms, but for this class, we're only going to talk about E1 and E2 and SN1 and SN2. Okay? So let's do a few examples, because you're not going to understand it just by watching me do it. So let's do some examples, and let's think about this. So let's say you have this particular alkyl halide, and let's say it's bromide, and you're going to react that with potassium tert-butoxide. I want you to draw for me what you think the major product is going to be. You can work with your groups. Get together. That's potassium tert-butoxide. That's a T. What's the first thing I need to do? Not gonna do the nucleophile yet. Remove the bromide?
Yeah.
And find the alpha carbon.
Find the alpha carbon. Remove the bromide. Find the nucleophile. Who's right? Rose is right. We're gonna, at least on paper, we're going to find the alpha carbon, right? And that's going to be where the halogen is. So I'm gonna mark it. And I'm gonna label it alpha. Okay? The bromine leaving is getting more into the mechanism. We're not worried about that yet. Finding the nucleophile is more about the mechanism. We're not worried about that yet. Right? We're taking the first steps first to identify what we think is going to happen. Once I've identified the alpha carbon, now what do I do? Yeah, I'm going to look and find out which of the beta carbons has the least number of hydrogens. So the thing that I always do first is I identify the beta carbons. And so I'm going to call this beta 1. I'm going to call this one beta 2. And I'm going to call this one beta 1 as well. Why am I calling these two things the same thing?
Because they are the same thing.
They are the same thing. They're both CH2s, right? There's actually a plane of symmetry. They are the same thing, okay? For all practical purposes, okay? So, I know I have a non-nucleophilic base, so I'm not going to do substitution chemistry. I know I've got to do some type of elimination. So what am I going? Where am I going to get the hydrogen from? Beta 1 or beta 2? What does Zaitsev's rule tell me? Yeah, beta 1, right? Does it matter which one I pick?
No.
Nope, not at all, right? So I'm going to predict that my major product deal. Just to show that everything's balanced, but this is the product that I'm interested in. Right? That's the elimination product that I'm interested in. It could be E1, it could be E2. I'm not asking that question. I'm probably not going to ask that question on the exam. I'm more interested that you know the substitution reactions. Okay? We want to work another one?
Yes.
All right. Let's do, let's see. And I'm going to put a triangle there for heat. That's what the little delta symbol usually means when it's over an arrow, is to heat it. That's not cyclopropane, that's heat. So let's go through the steps again. What's the first thing that I need to do? Find the alpha carbon. Where's the alpha carbon? Okay, the carbon with the halogen. In this case, it happens to be Cl, so I'm going to label it. And now I've got my beta carbons, right? How many beta carbons do I have? I've got 2. I've got beta 1 and beta 2. Beta 2 has a hydrogen on it that I'm not showing, but it's there. Okay, I'm reacting this with sodium hydroxide and I'm heating it. What do you think the product is? Where would you draw the carbon-carbon double bond? Between alpha and which beta carbon? Did I hear 3? Yeah, we've got 2, right? So it can be between alpha and beta 1, or it can be between alpha and beta 2. So I've got to ask myself, whose rule? Zaitsev. So is Zaitsev's rule going to tell me beta 1 or beta 2? Beta 2, right? And I'm only going to draw the organic product, not the byproducts in this one. And that's going to be my major product. Okay? You might be asking yourself, why didn't it just do substitution? This could be a nucleophile, right? This is a pretty good nucleophile. Why didn't it just do substitution and do this? Why didn't it do that? Hydroxide is a good nucleophile. It's charged. It likes to do SN2. Okay? SN2 likes to have primary alkyl halides, not secondary. This is a secondary alkyl halide. Secondary alkyl halides can do SN2, but it's slower. And there's a little thing that I haven't told you about yet. I told you here that there was heat. Anytime you have a choice between a substitution reaction and an elimination reaction, temperature comes into play. And temperature, if you heat it up, almost always favors elimination. If you wanted the substitution reaction to occur here, you would have to do it at lower temperatures. Okay, so temperature plays a role in whether or not you have elimination versus substitution. So looking at this problem, I know that I've got a base that can also be a nucleophile, and I have to look further at the conditions. And I know that I'm heating it, so I'm going to favor the elimination process, not the substitution process. Okay?
So for the purpose of this class, can I just assume that if heat's involved, it's elimination, not substitution?
Probably for this exam you
For
can,
this exam, okay,
but I don't know about the rest of the class.
fair enough.
Can you explain one more time 6?
Zaitsev's rule?
Yeah.
Yeah, so Zaitsev's rule says to look at the beta carbons, and the beta carbon with the fewest hydrogens will lose the hydrogen. So that beta carbon is where I'm going to form the double bond between that carbon and that alpha carbon. That's what Sykes-Head's rule tells me. The way that I like to think about this is the one with the least loses. Okay? The one with the most gets to keep it all. Doesn't sound quite fair, but that's the way it turns out in nature. And the reason that that turns out to be the case here is because losing this hydrogen gives me the more substituted alkene. This is a tri-substituted alkene. If this beta carbon lost it, I would only have a monosubstituted alkene. More stable, less stable. Right? That's why Sykes-Head's rule works. It's all about alkene stability. Let's do one more, and then we'll move on to today's new material. So what is the first thing that I do? I find the alpha carbon. Which one is it? The one with the halogen. This time it happens to be iodide, right? So there's alpha. Now what do I do? I find my betas. How many betas do I have? I have two. I have beta 1 and I have beta 2. Now what do I do? Okay, how many are there? How many hydrogens does beta 1 have? 3. How many hydrogens does beta 2 have? 0. So in this particular case, the only elimination product I can get is that one. It's all that's possible. There's no hydrogen on beta 2 to eliminate. Okay? So it's very important when you identify your beta carbons that you are able to count the hydrogens that exist on that. And remember, I don't explicitly draw them out. We use the bond line structures, right? So you have to be able to do that. Any questions? A lot to come back from spring break on, isn't it? All right, we're going to get started in chapter 8 today. We're going to talk about alcohols and ethers. The chapter also talks a little bit about thiols. And we'll talk maybe a little bit about it, but if you know your chemistry of alcohols and ethers, usually you can get the thiol stuff pretty easily because oxygen and sulfur are in the same family on the periodic table. So very similar. So I think we all know about alcohols a little bit, right? We come into contact with alcohols in our daily lives, right? You go pump gas, the sign says contains 10% ethanol. You go into your bathroom in the morning and you use rubbing alcohol for various things. You know, at the end of a tough day, you may go to the bar and get a drink, right? If you're old enough, right? So there are alcohols in our everyday life. And there are ethers in our everyday lives too. You just don't come into contact with them as much, okay? You just don't come into contact with them. But they are around us everywhere, and they're very useful materials that we need to spend a little bit of time talking about, okay? So, you all know what an alcohol is at this point. It was one of the early functional groups that we learned about, right? The alcohol has the hydroxyl, the OH group. So that's the functional group attached to a saturated carbon. So for example, we could have this, right? That is an alcohol, where we have an R group attached to an OH, right? And so any R group attached to an OH, we call that an alcohol. We can actually have the R group be an alkene. Those are called enols. They have different types of chemistry that we're not really going to talk about too much in this class. But if you go on to higher organic chemistry classes, you'll learn an awful lot about enols. They're a special alcohol. And you might also learn about so-called phenols, where the OH is attached to like a benzene ring. We're going to learn about benzene in another chapter. But these alcohols behave differently than your ethyl alcohol that you might like to consume. Okay? You wouldn't consume a phenol. Okay? They can be toxic. Enols can be toxic. And so can other alcohols. I mean, ethanol's toxic. And when you're drinking a beer, you're drinking poison. But poison is all in the dose. Okay, so here's some examples. How would you name that, you think? CH3CH2OH. CH3CH2 is what kind of group? If you were naming it an alkyl group, it would be ethyl, right? That'd be an ethyl group. This could be ethyl alcohol or ethanol, okay? So when you go pump your gas, right, it says contains up to 10% ethanol. That's corn alcohol. It's also known as grain alcohol, right? So if you're out in the backwoods and you run across a still, this is what they're making, right? This is moonshine kind of stuff, okay? And so there are a couple of ways to name it. The most common is people will call this ethanol. Ethyl alcohol would also be an appropriate name. How about this one? Most of you probably have a little square bottle of this. It's about a quart size in your bathroom. This is rubbing alcohol. It's called isopropyl alcohol or isopropanol. Okay? Or 2-propanol, right? Notice that we have to have a number here now. Why do we have to have a number here? Yeah, there's two different places the OH can be attached to. It can be attached to the primary carbon or it can be attached to the secondary carbon, right? So there's two possibilities. Even though there's 3 carbons, there's only 2 possibilities for where the OH can be, right? Either on the primary carbon or the secondary carbon. Why do you think we'd name that? I have 5 carbons in a ring. What would we call that if it's just the 5 carbons? That'd be cyclopentane. I saw somebody know that, right? So if this is cyclopentane, I put an alcohol on it, what do you think we're going to name it? Cyclopentanol. Yes, we can just name it cyclopentanol. That's right. Do I need a number for that? Why don't I? No matter where I put it, it's cyclopentanol, right? 1 cyclopentanol is redundant. Because 2 cyclopentanol doesn't exist. If I put it on the number 2 carbon, it becomes number 1, right? So those are just some examples of alcohols that you all might be somewhat familiar with. Ethers, right, contain oxygen, but instead of an OH, it's just the oxygen between 2 carbon atoms, right? So ROR. So R and R prime, as we have here, can be alkyl, alkenol, can be aryl, can be any kind of R group, okay? For all practical purposes, right? They can be the same, they can be different. Here's some examples, okay? This is called dimethyl ether because we have 2 methyl groups attached to it. This is an ether where the oxygen is attached to an sp2 hybridized carbon and an sp3 hybridized carbon. Here's an example where we have a benzene ring and a methyl group attached, but they're all ethers. They are all ethers. Okay? Does anybody know what the most common ether is that you might have heard about in history? It's diethyl ether. Yes, so 2 ethyl groups. Why is it so common and famous, might you think?
Wasn't it used for Oxidation.
Was, yeah. Back in the early 20th century, maybe? Maybe even the end of the 19th century and early 20th century up until probably the 1950s, I would wager. I don't know my history on this particularly well, so don't take this literally. But, you know, if you went in for surgery prior to that, it was gonna hurt. They were gonna be cutting and prodding and poking and sewing and all kinds of stuff while you were, at best, half drunk, to where it didn't feel so bad, or you were awake and you were feeling excruciating pain. Can you imagine what it would have been like to be a soldier in the Civil War battlefield where they were literally amputating in the field with no anesthetic whatsoever to save your life? Today, we have access to things that make our lives way better. Way better. Even when you're in a bad situation today, you are way better off than you were even 60 years ago. Today, average people have access to health care that multimillionaires didn't even have access to 60 years ago. Long way we've come. And we've come this way because of chemistry. And I'm just bragging a little bit on that, but it's true. We have medicines and things now. Diethyl ether was one of those first ones. Okay? And so they would soak cotton balls in this diethyl ether, they'd put it over your face, you'd breathe, you'd go into a state of anesthesia, they could do their operation. The problem is diethyl ether is highly flammable. People caught on fire during their operation, not a good idea. You also may have heard, if you have grandparents, or maybe even your parents, if they happen to live on a farm, for example, and they have an old tractor that's hard to start, they will use starting fluid to help start it. That's diethyl ether. They spray that in there, it's very volatile, it catches fire very easily, it helps those engines start. Okay, so if you happen to ever see somebody use starting fluid, they're using a sprayed can of diethyl ether. Okay? Let's talk a little bit about some physical properties of alcohols. Okay? So it turns out that alcohols can be soluble in water, but they may not be. Okay? And we all know this, right? You go to the bar and you order a mixed drink and they take your favorite gin or whatever and they mix it with something else and it's all mixed together, right? We know that ethyl alcohol is perfectly soluble in water. We know that rubbing alcohol is perfectly soluble in water, right? You're in front of your mirror, you're doing whatever you're doing with your rubbing alcohol and you wash your hands, it comes right off, right? No problems whatsoever. You don't worry about having 2 layers or anything like that, okay? And so it turns out that the smallest alcohols, usually up to 3 carbons, we consider to be completely soluble in pure water. So methanol, CH3OH, ethanol, CH3CH2OH, propanol, CH3CH2CH2OH, isopropyl alcohol. Those are usually considered to be completely soluble in water. Meaning I can take equal volumes of alcohol and water, mix it together, they completely dissolve. Okay? And you can get solubilities from C4 to C8, you can get some alcohol in water. Okay? You can start to get some alcohol in water with those as well. Okay? And so here's some examples. Right? So this is methyl alcohol or methanol, the first one. It's also called wood alcohol. This is the byproduct from making moonshine that causes you to go blind. This is why if you buy illegal moonshine, make sure the person knows how to make it, because that stuff will cause you to go blind, right? These are completely soluble. This one, however, these over here have differing solubilities. Okay, so for this one, what would you call that one? How many carbons? 4. What's the parent? Butane. We're going to drop the A and E ending and put OL for the alcohol. So this is butanol. But I need a number now, don't I? This is 1 butanol. Okay? So 1 butanol, I can get 8.3 grams of 1 butanol into 100 milliliters of water. So weight to volume, that's about 8%. We'll just call it If I go to the next one that we see here, how many carbons do I have there? 2, 3, 4, 5, 6, 7, 8, 9. Yes, so this would be,
One nominal.
nonane would be the parent. Yes, so it would be 1 nonanol. Nonanol, right? You can only get 0.05 grams of that into 100 milliliters of water. So would you call that soluble? I would. I mean, yes, you can get some in there, but I wouldn't call that soluble at all. This is completely soluble. This is partially soluble, and I would say that this is insoluble. Can you think of a rule to come up with? I call it my rule of thumb. I haven't told you what it is yet. Something you're going to want you to remember. But looking at all that, what could you tell me your rule of thumb might be? If you had to develop your own rule of thumb, what would you say?
The more carbon is the less oxygen.
True. That's a true statement, but could you draw a line? Could you tell me about where you would draw the line between soluble and insoluble? How many carbons would it roughly take? Close. 5. Yeah. I call it my 5 carbon rule. For every OH group, if I have 5 or fewer carbons, I'm going to predict it to be completely soluble in water. There are examples that go against it. It's a rule of thumb. It's not a law. Okay? So, for example, let's look at an example. Soluble or insoluble? Insoluble. I've got 1 OH and how many carbons? 6. Does that satisfy my 5 carbon rule? No. So it's going to be less soluble than this for sure. What if all of a sudden I did this? Is that soluble or insoluble? What does the 5 rule carbon? What does the 5 carbon rule say? Per OH. So how many OHs do I have? I have 2 OHs. How many carbons do I have? 6. That's a 3-to-1 ratio. It satisfies my 5 carbon rule. Okay? If you all have ever taken Miralax, anybody know what that is? It is a polyol, and it has a huge molecular weight, and it is completely soluble in water. Why is it completely insoluble in water? Because it has a lot of alcohol groups. It satisfies the 5 carbon rule overall. So even though it weighs, I don't know what the molecular weight of it really is, it's really high. Well, it's a polymer, okay, essentially. But it has a lot of alcohol, so it's perfectly soluble in water. You drink it, it makes you go to the bathroom. It works really well, okay? Now, one of the things that I've talked about here is that solubility in pure water. What do you think happens if I don't have pure water? Is it going to be the same or different? It's going to be different. And in fact, I've got this little bottle here to show it. So, looks like it's one liquid, right? Looks like I've got 2 different kinds of beads in there, right? Watch what happens when I shake it up. Notice the beads are all organizing, and now the white beads are going to the top, the blue beads are going to the bottom. What is that all about? What's happening? Can anybody see what's happening? Is there one liquid in there or 2? There are 2 liquids. They just happen to have what's called the same refractive index. So you can't really see them very easily. And so we put these beads in there to help. So we have a liquid that's less dense, and that's where the white beads are. And we have a liquid that is more dense, and that's where the blue beads are. And they, as the phases separate out, you see where they meet kind of in the middle. Turns out this top layer is nothing but your good old friend rubbing alcohol, 2-propanol. The bottom layer is water. Well, wait a second. I just told you that isopropyl alcohol and water are perfectly miscible, right? They're soluble, and they are. This happens to be water that is saturated with salt. It is sodium chloride, it's brine. The alcohol is not soluble in concentrated brine. Just concentrated salt water. Anybody know why? Look at that. Joy. Why do you suppose the alcohol is not soluble in salt water?
Because there's already salt in it.
Mhm. That's true, but why?
NaCl is already attached to the H2O.
Okay, yeah. What else?
It can't form hydrogen bonds.
Yep. You all are saying the same thing at different levels of understanding. Absolutely. So the salt is in the water, and the water is associating with the salt. It's solubilizing the salt, so it doesn't have the ability to do that with the alcohol. It's all about hydrogen bonding. And the more carbon that I have on here, the less likely this alcohol can form stable hydrogen bonds with the water and go into the water layer. Okay? That's the take-home message. The more carbon that you have per OH group, the less likely it is to be soluble in water. You need to remember that rule of thumb. I guarantee you there will be a question on the exam where I will say, give you some alcohols and ask you which one do you expect to be the most soluble or the least soluble or something like that. Okay? There will be some type of question about that on these. Okay? So we learned that there's got to be something with hydrogen bonding. We see that with that little bottle experiment, right? There's got to be something going on with hydrogen bonding. And so if you look at something like methanol, it can form hydrogen bonds with itself. It can also form hydrogen bonds with water, and it's pretty small, so it can go into the water layer quite easily. What you'll notice is that primary alcohols tend to be more soluble in water than secondary alcohols, than tertiary alcohols, and it's because of the steric effect. The more carbon I put around the alcohol, the less likely it is to form a hydrogen bond with water. Okay? So tert-butanol, for example, would satisfy the 5-carbon rule, and you can get some of it in water, but not a lot because it's a tertiary alcohol. Isopropyl alcohol, what you just see there in the bottle, if you add some salt, all of a sudden it's no longer soluble in water. But I can't do that with methanol or ethanol. If I take methanol or ethanol, even if I add salt to it, it will be soluble in water. Okay? So, trying to come across here telling you that structure is important. Okay? The functional group in all of them is the OH group, but it depends on, the physical properties are going to depend on what is attached to that carbon that the OH is attached to. So it's important to be able to identify those. Okay? So, if we look at some compounds here, don't worry about the word epoxides, it's just another name for an ether. This came out of a different book, but I like the table. What can you tell me about these 3 compounds? What's similar? Go ahead, I'm sorry, I interrupted you.
I did the same thing.
Oh. What do you think's are pretty close to similar about all 3 of those? They all weigh about the same. If you calculated the molecular weight for each of these molecules, you would find that they have about the same molecular weight. Okay? What's different about them? The functional group. What's this functional group? It's just a good old alkane, isn't it? Just a pure hydrocarbon. What's the functional group here? ROR is ether, and here we got what? An alcohol. What do we notice about the physical property measured here as boiling point? It increases. Notice, this has about the same molecular weight as this. This boils at 0 degrees Celsius. This boils at 97 degrees Celsius. That's a big difference. Right? All this one has is van der Waals forces. Right? That's all. That's the only thing it can do to interact with itself. It's not polar. Right? This is polar. Right? So it's got dipoles. We get an 11-degree increase in the boiling point by just having a dipole in the molecule, because dipoles can interact with dipoles. Now we have a molecule that can hydrogen bond, right? Can form hydrogen bonds with itself or with water. Notice what happens to the boiling point. So what does that tell us? It tells us that hydrogen bonds are relatively strong. So the ability to form hydrogen bonds means something, right? And so here now I take all these alcohols that have the same molecular formula, okay? They've all got 4 carbons. They've all got one OH group. This is a tertiary alcohol, this is a secondary alcohol, and this is a primary alcohol. They all have the same molecular weight, they all have the same functional group, they all can form hydrogen bonds, and yet they all have different boiling points. Why? Because the tertiary alcohol has all this junk around it, and it can't form a very strong hydrogen bond. I can't get 2 molecules of the alcohol very close to one another. The secondary alcohol has less junk around it. It can get a little closer, so the boiling point goes up. That means the bond is stronger, right? And this one being primary, this can form very strong hydrogen bonds, okay? And so you go from 83 degrees Celsius to 98 degrees Celsius to 118 degrees Celsius, simply by forming stronger hydrogen bonds. I've probably told you in the past that alcohols are nothing more than organic versions of water. Water is important for life. You know, oxygen only weighs 16 and hydrogen only weighs 1. The molecular weight of water is only 18 grams per mole. And yet it boils at 100 degrees Celsius. Thank God for us. Because with that molecular weight, at the temperature that the Earth is, water should be a gas. It weighs about the same amount as methane. Methane's a gas. But yet water is liquid over a vast temperature range because it can form hydrogen bonds. Okay? It's the same thing that you're seeing in alcohols. It just happens to have some organic stuff associated with it. Here's that 5-carbon rule, right? So you can look at that later. So you're going to find that alcohols and ethers are going to be soluble in organic solvents, things like dichloromethane and hexane and other things. You're going to be able to dissolve alcohols in those. But you can dissolve them in water if they satisfy that 5-carbon rule. You're going to be able to dissolve ethers in water if they satisfy that 5-carbon rule, okay? And so it turns out to be an important thing because there are alcohols and ethers in biological systems and they need to be able to be soluble in water. It's very important, right? All right, so let's talk a little bit about naming. I'm not going to spend too much time on this. We've already kind of worked our way through it. But there is something very, very important that you need to know. And that is that the alcohol OH group is a privileged functional group from a naming perspective. Remember when we were naming alkyl halides and alkanes, right? We had these rules, and a halogen was a halogen, and if it happened to be, you know, the numbering happened to work out, then it just worked out the way that it did. In alcohols, you always number your carbon chain such that the alcohol has the lowest number. It is different than every other functional group in that regard. Alcohols, if you can number it 2 ways, you're going to number it the way that gives the alcohol the smallest number. That's the rule for alcohols. It's privileged. Okay? So, I want you all to take about 5 minutes and I want you to do the first 3. I want you to name those alcohols. Get in your groups.
I didn't get that. Could you try again?
Nope. Everybody had a chance to? When I get bored, I watch it. How do we name the first one? One what? Heptanol? How many carbons do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, right? So that, remember that C6, or that little 6, those CH2s? There's 1, 2, 3, 4, 5, 6 CH2s. That's what that parentheses is representing. It's okay. But I think you said it right once you realized there was 8, and what is it? 1 octanol, right? 1-octanol. What does the 1 tell me? It tells me where the OH is. Right, so I could have 1 octanol, I could have 2 octanol, I could have 3 octanol, I could have 4 octanol. Can I have 6 octanol? I can't, because we always want to get the lowest number, right? How about this one? What's the parent? I'm counting 5, right? So it's going to be a pentanol, right? So am I going to number from left to right, or from right to left? And why? That's right. If I number this way, the alcohol's on carbon 4. If I number this way, it's on carbon 2, right? So this is what? 4 methyl, 2 pentanol. All right, very good. And what about this one? What's the parent? Cyclo. How many carbons are in the cyclo? Cyclohexane, right? So this is a cyclohexanol, right? So there's my parent. So now how would I name it? 2-methyl 1-cyclohexanol. Now in your book, they leave the 1 out, although I think this is the more correct way to do it, okay? Because I could technically have 1, well, actually, no matter where I move it, it would always be number 1. So they're okay, I mean, it's okay to leave it, but they're technically correct, right? Because no matter where you put it on this molecule, the alcohol will always be number 1, okay? So we'll do that. Is that all I need for that name? If this was a test, I'd count it wrong. Why would I count it wrong? I have to put the cis or trans in there. And what is this one? The OH is coming out towards me. The methyl group is behind. These are what? These are trans. So this would be trans 2-methyl 1-cyclohexanol. Okay? These are also chiral centers. I could ask you to tell me what's the stereochemistry at each one of those carbons. That's possible. Okay? Now let's look at these 3. Of the 3, does any of them satisfy my 5-carbon rule? No. So we would predict they would be very insoluble in water, or they'd be insoluble in water. But what if I asked you to rank them in terms of their solubility in water? Which one would you say is the most soluble? The one with what? The one with 5 carbons? Okay, how many carbons total is here? So there's 6 total carbons here, right? So that's, you're getting to it. Let's count the carbons, right? How many total carbons do I have here? 7. How many carbons do I have here? 8. How many OHs do I have for each one of them? 1. So it's 7 to 1, 6 to 1, 8 to 1. So now if I asked you to rank these in order of solubility, what would be your ranking from least soluble to greatest, or to most soluble? What would be the least soluble? Least would be A, the next would be C, and then it would be B. Okay? Fractions are important.
So the rule of thumb, is it 5 or less or less than 5?
5 or less per alcohol or per ether group. Yeah, so it's 5 or less. 5 or less. All right, good work. So let's talk about some interesting alcohols. Of course, we've already talked a little bit about ethanol, probably my favorite alcohol. I like wine, I like bourbon, right? That's what all of these things have. The source of the alcohol is different for the different alcohols. Wine comes from grapes. Bourbon comes from grains. Vodka comes from potatoes. Sake comes from rice, right? They're all carbohydrates that lead to these things, but they lead to different types of beverages, okay? Methanol, it's also called wood alcohol, right? This is an alcohol that is very, very useful. We use it all the time in the lab. It's a good solvent. It's flammable, so you can use it for a variety of things if you want to burn things. Formula One race cars run on methanol. That's their fuel. They don't run on gasoline. They run on methanol. They're methanol powered. And so it is a pretty good fuel. So you might be asking yourself, why don't we run our cars on methanol? It turns out that Formula One race cars cost millions of dollars for a reason. And one of those reasons is that methanol is very corrosive. You have to use special materials in your engine to run methanol. You can't just take a Chevy big block and put in there and run methanol through it without a lot of modifications. It's just not feasible. 2-propanol, all right, let me finish up with methanol. So if you have ever watched Moonshiners, anybody in here ever watched the show Moonshiners on Discovery Channel? Yeah, so a couple of you. What do they always do when they first do that, the first part of their distillation? They get a small amount of stuff and they do what with it?
Toss it out.
Toss it out, and they call it
Heads.
the heads. The heads, it just means it's the stuff that comes out first, okay? But even in the chemistry lab, we frequently will throw the heads out when we're doing the distillation. That's because the heads contain all the methanol. Methanol boils at a lower temperature than ethanol, and they take all this grain that has woody stuff in it. So the yeast is making both ethanol and a small amount of methanol. And so if you were to drink those heads, you would go blind, because it only takes 15 milliliters of methanol to cause you to go blind. And 100 milliliters, if you drank what would be a glass full of methanol, you'd die, okay? This does happen. People accidentally ingest methanol, especially young children. Methanol is quite frequently found in the home. Especially if your father or mother or whatever likes to do a lot of woodworking, they'll have this alcohol around to do stuff with wood, okay? What do you suppose they do if a child ingests methanol? What do you think they do when they get to the hospital? They pump them full of ethanol. They make them drunk. So that your liver works on the ethanol and not the methanol. And so that the methanol can get excreted. So that's the only real way that you do this. Essentially you're using Le Chatelier's principle, okay? 2-propanol, you all know about that one. And then this is ethylene glycol. This used to be used in antifreeze. If you have a car that has the old yellowish fluorescent green antifreeze in it, that was what was in it, was ethylene glycol. Now your cars probably have a pink stuff in it. It's called propylene glycol. The reason that we don't use ethylene glycol anymore is because, even though it's a really great antifreeze, it is extremely sweet tasting. Do not do this. I've actually taken, and it is very sweet, sweeter than sugar. And so old shade tree mechanics, when they'd change their antifreeze out of their car, they'd put it in a bucket and they'd set it aside, and the neighborhood dog would come up and lick it and then die. Kids would get a taste of it, oh, that's, and start drinking. And it will kill you, okay? So we don't do it anymore. But interestingly enough, you put one more carbon in between these two carbons, it's not toxic. It's interesting, huh?
That's sad.
It is sad. That's why we don't do it anymore, right? We learned, yeah.
Isn't ethylene glycol like an ingredient in some stuff? Like I feel like I've seen it on the ingredients list.
Probably not ethylene, you've probably seen propylene glycol.
Maybe.
Yeah,
Yeah.
propylene glycol in small quantities is food safe, if I remember right. Don't go drinking propylene glycol either, but there's also some interesting ethers. These are so-called 18 crown ethers. We'll pick back up with this on Thursday. We have finished chapter 7, so that should tell you something about a quiz on Thursday. So have a great rest of the day, and I will see you all then.